Hi, welcome back. Last time we talked about Lagrange multiply method to solve optimization problems. And today we're going to learn linear programming and the simplex method. And we'll see the difference of the model. So there's a little element in the Lagrange multiply method. It's not so realistic. That is the constraint. You assume all the constraints are equations. But in reality, that means you have to use all the resources you have. That's not realistic. You only need to make sure not exceed to the resource you have, but you don't have to use all of them. So a little change to the model, we change some equations into inequations. And then we're going to use the linear programming method to solve it. When we say linear, that's an assumption. The objective functions, constraint equations, and the constraint inequations are all linear functions. That means all the variables are first degree. And when we proceed of this course, you will learn the more tools in mathematics you learn, and the more realistic problems you will know how to solve. And first, let's look at a typical problem. A typical problem will give you the resource you have, such as in this example, your company decided to invest 12 million to acquiring new machines. And there's a few choices you could make. And in here, we assume you have three types of models, A, B, and C. For each choice, you're going to consume some resource, such as the labor. You have a total 100 of operators you can hire. And the operation room, maybe you have so much floor plan you can put the machines. And the financing investment limits, and you have $12 million. And your objective is to maximize your productivity of those computer boards. And it told you the productivity per hour, per day, and you can put it together an objective function. And that's a typical problem. Or another example I'm going to show you, assume you run a small farm, you have some capital investment, and you have limited acres of land, and you have limited hours to work in the farm. So how can you grow the most profitable crops? Then you can maximize your profit. So those are typical questions, very realistic in the business. So now, a typical questions have four major components. First, you have so-called design variables, x, y, z. That's the quantity you're going to find to maximize your objective function. Well, sometimes in business, we call it control variables. Next, you get your objective function f as the function of x, y, z. Typically, we're going to use the capital letter X as a vector. This X is X, Y, Z, could be more variables. And we always try to minimize. You can easily change maximize to minimize by negate this function. And then you have a set of constraint equations, a set of constraint inequations. That's the new element, different from what we learned last time. So let's look at the mathematics expression. The canonical form, you got the n variables, x1 all the way to xn. You can write as 1 column vectors. N could be 2, 3, 4, depends on the complexity of your question. And then you get m constraint equations and the L constraint inequations. Pay attention. See, this is equality, this is inequality. That makes your problem more realistic. So now, with all those constraints, you're going to try to find your minimized solution. Well, we have a few well-posed problems. Itself must be an intelligent work from well-trained professionals. So a well-posed problem is a mathematics model. It usually either have multiple solutions with the same maximum and minimum, but have different points to achieve the same goal. Or even better, you have a unique solution. That means you only got one point of x, y, z to achieve the maximum solution or minimum solution. Well, ill-posed problem could have all different contradictions or confusing, or in a situation you don't have any solution. The most common problem is the ambiguity. Well, unless you are very well-trained professional, just like you use the casual English in daily life, your problem itself is ambiguous, means there's different way to interpret what you really asking for. So there's no way you can specify a correct mathematics model. And the second, you might have specified the problem very well, but the constraint equation contradict each other and lead to the situation like x plus 1 equal x plus 2. Of course, that's a contradiction itself. You don't find any solution. Well, another situation is you don't have enough constraint lead to no bounded solution. Means if I don't have any constraint, I can make x, y, z equal infinity. That's not a real solution in the real engineer or business world. Let's look at the graphic demonstration. If the problem is in 2D, and those diagrams, sometimes we call it a polygon. The polygons is so-called feasible domain of your solution about the x and the y. And typically, those straight lines are the constraint equations or inequations. Those corner points, we call them extreme point. Those are the point satisfy two constraint equations. Usually, if you achieve maximum or minimum, you're going to run out of more than one resources. And that's when the extreme point happened here. and your optimized solution most likely occurs at the extreme points. In other words, those corner points. If you consider a problem in the 3D, then you got this convex, we call it a polyhedron. The polyhedron in each plane will correspond a constraint equation or constraint inequation. And then each line will related to 2 equations. And those vertices were related to 3 at least of those equations. We call those vertices as extreme points. And then you are going to look for the optimization solution at those corner points. We call it extreme points.